This ShowMe is a response to a question from one of my students. She's concerned about three particular exercises where the textbook is instructing the students to use mental math to find the value of squares. And the three squares in question are 61 squared, 48 squared, and 499 squared. And the book expects the students to use a pattern in the section, so I'm going to demonstrate how to do that in this ShowMe. To do 61 squared, we have to recognize that 61 is actually a sum. It's a sum of two numbers, and we want to pick two numbers whose properties and facts and squares particularly are easily accessible, mentally accessible. Well, the best choice I can think of is 60 plus 1. So we're going to rewrite that as 60 plus 1 squared. Now there's a pattern for this in the particular section textbook that we're talking about. In the textbook, it's demonstrated that if you take a plus b as a binomial and square it, the result using the flow method and combining like terms is a squared plus 2ab plus b squared. The book recommends, and I have recommended in class, that my students should memorize this pattern, not only because it makes these calculations easier, but it also makes it easier to factor when this pattern is seen in other places. Anyway, to use this, then we have to acknowledge that 60 is being cast as A, and 1 is being cast as B. So we could, if we were not going to use mental math, we could simply have 60 squared plus 2 times 60 times 1 plus 1 squared. And if you follow that through to its logical conclusion, you have 3600 plus 120 plus 1, which is 3,721. There's an insight here that may not be obvious, but it's really, really interesting. And that is that this is always going to happen when you are dealing with consecutive square numbers. That is, when you're dealing with 60 squared, as we are here, and then 61 squared, which is what we're trying to find. It turns out that the difference between two consecutive square numbers is always an odd number that you can make out of this smaller number. So if we want to know, knowing what 60 squared is, being 3,600, if we wanted to know quickly what 61 squared was, the fastest way to do it is to take 60 and make an odd number out of it. And the fastest way to make an odd number out of any natural number is to double it and add 1. So this will always work. So if I wanted to find out what 62 squared was, now that I've got this particular information, it's actually quite easy. I take 3721, which I know to be 61 squared. I'll add 2 times 61, which is 122, and then I'll add 1. And that's 3,844. And I assure you that's correct. That will always work. Now, as far as the mental math is concerned, how were you supposed to be able to do this? Well, you were supposed to be able to organize your mind so that 60 squared, which is relatively easy to manage, 3,600 was in your mind already. Then you recognize the pattern. You double 60, which is 120, not too hard to do in one's head, and then add 1 to get 3,721. Is it a tall order for most folks? Yes. But here in the algebra, here in the math club, we're not just most folks. We're supposed to be able to do some of this stuff in our heads. So that's what the book was trying to challenge my students to do. I don't know that it's a great exercise, but it is certainly an application of the pattern. This one's a little bit different in that you're not going to exploit familiar consecutive squares this time. I don't think anybody is walking around having memorized 47 squared or 49 squared. But there are squares we can use to make this square that are very familiar to us. You might say from the previous example that we should be using 40 plus 8 to represent 48. That would get it done, but it's not the easiest mental math to do. Far better, in my opinion, would be using 50 minus 2 squared. I'm quite sure this is what the authors of the textbook intended, because they taught us, or they presented to my students, a pattern for a difference of two numbers being squared. And it's very much like the pattern for one that's a sum. The only difference, of course, is that the middle term is negative. So in this case, 50 is cast as A, 2 is cast as B. Well, 50 squared is pretty familiar. That would be 2,500. You're going to subtract twice 50 and then times 2 again. So that's going to be 200. That's not too hard to manage mentally. And then plus 4. So the answer is going to be 2,304. That is something that I think is pretty reasonable for one to do in one's head. That's why the mental math thing makes sense here. There isn't a special consecutive numbers trick to employ in this situation. Just the discipline to see that 48 is 50 minus 2. Take 50 and square it in your head. Subtract twice 50 times 2, which you need to know is 200, and then add 4. I don't think any of that is too much to ask someone to do in their head, but they are going to have to be very, very familiar with this pattern in order to do it. And since I've recommended that my students should memorize this, I think that's a reasonable thing. However, it's going to take some practice. I don't know that it's a heavily valuable skill out there in the workplace, but it's never a bad thing to be good at figures. 499 squared then works very much like the example I just showed. You need to recognize that 499 is 500 minus 1, and then employ the pattern. The pattern said that the first part is going to be 500 squared. The second part is to subtract twice 500 times 1, which is 1,000, and then to add 1. Well, 500 squared is 250,000. Take away 1,000 and add 1. That'll be 249,001. And it's a mental math exercise because that's not terribly hard mental arithmetic to do. It does, however, require some discipline, and you do have to be very familiar with the idea that squaring a minus b produces a squared minus 2ab plus b squared. So I hope that answers my student's question. I hope that that clears it up. I don't mind showing some work on mental math questions. I'm not going to look over the assignment and take off points or credit for someone who does show the work, but I would like to see at least that each student understood that this pattern was to be employed. So I hope that clears it up and hope reveals some more insight into the basic pattern for squaring binomials.